All right, so I'm going to describe our recent work on skyrmion dynamics, namely on the question of whether skyrmions are massive or massless. That has been a little bit controversial over the last few years. It's a new mechanical model that we introduced to capture its behavior, which is a little bit more universal than the one that just includes a massive skyrmion particle. Here's a summary in case you have to run. Skyrmion and magnetic bubbles, which were their predecessors, are often modeled as point particles, and their dynamics depends on the details of how you coarse grain their motion. If you treat your skyrmion as a rigid soliton, then its dynamics is massless. You apply a force and you get a velocity, no acceleration. If you go one step beyond that and do a more sophisticated analysis where you define the skyrmion position as the center of skyrmion density, that also gives you a massless dynamics. However, if instead you use the longitudinal magnetization mz as the weight, you get a massive dynamics, or sometimes a massless one, depending on the nature of the applied force. And that's what I'm going to discuss today. The new mechanical model that we proposed has two massless particles, one of which is visible and the other is not. They are coupled through a gyroscopic and a potential term between them and to an external force, either one of them or both. And so that model works pretty well for modeling skyrmion dynamics. We have a paper with Xiaofan Wu, a graduate student in our department, that came out recently in SciPost Physics. So modeling a skyrmion as a point particle goes way back to the 1970s when Al Thiele introduced his very nice approach to modeling soliton dynamics. He said, suppose we translate the Landau-Lifshitz equation shown here into the equation of motion for the center of the soliton that moves without any deformations in such a way that it just gets displaced, and the displacement depends on time. Then you get the Thiele equation, which is shown here without dissipative terms. And Thiele equation gives you equilibrium between forces acting on a soliton. F is a force that comes from some potential energy of the soliton. And the first term, g cross its velocity, is a gyroscopic force, or the gyrotropic force, the analog of Lorentz force, or Magnus force, or Coriolis force in mechanics. This equation describes a massless particle with an electric charge that moves in the background magnetic field G, and G is called gyro vector, and you can calculate it from the properties, from the shape essentially of your soliton. Later, Nikos Papanikolaou and his students introduced the more sophisticated approach where solitons are deformable. They need not keep their shape, so the rigid motion approximation need not be made. But still, if you define the position of your soliton, in this particular case, in 2 dimensions, it would be a skyrmion or maybe a vortex. You can define the position of the skyrmion by using the skyrmion density rho, given by this expression, as the weight, and its integral over space gives you the skyrmion charge, plus or minus 1 for a skyrmion, plus or minus yeah for a vortex. And its first moment gives you the position of your skyrmion. And it turns out that position of the skyrmion so defined obeys the exact same Thiele's equation. Even though your soliton may be deformed, nonetheless, this position follows the same equation of massless dynamics. An alternative approach was proposed by Ivanov and others in 2005, which is more convenient experimentally because skyrmion density is not easy to image by experimental techniques. So what you could do instead is you could use one of the components of magnetization, let's say the longitudinal component mz, and use it as a weight to define the total magnetization of the skyrmion relative to the background magnetization, as well as the first moment would be the position of the skyrmion. And it turns out that in many cases, this definition gives different types of dynamics. The Thiele equation acquires a non-zero left-hand side, which is given by mass times acceleration. So this looks like a massive particle in the magnetic field and whatever external force that acts upon it. So the difference is illustrated here. This graph is taken from a nice paper by Papa Nicolaou, again, and his former students, Stavros Kamenets, in which they applied the gradient of a magnetic field to drive a skyrmion. And depending on how they defined the position, if they used the skyrmion density to define a position, then they got a straight line. When the force points in the y direction, the skyrmion is moving in the x direction, this black straight line. And when they used the magnetization as a weight, they obtained this different dynamics, which involves these Larmor oscillations at the frequency given by the ratio of the gyroscopic coupling and the mass. So the Larmor oscillations are a good sign that your particle has a mass, because the frequency is determined by the ratio of the magnetic field and the mass. And so their presence indicate that your particle has inertia or mass. So here's a simulation of the motion of a magnetic bubble or skyrmion in a disk performed by Büttner et al. In 2015. It's an experimental group, in fact. They studied the motion of a skyrmion. And again, as experimentalists, they used the simplest measure to determine the position of the skyrmion, which is the weighted longitudinal magnetization. So roughly speaking, you just follow the center of this red bubble, and that's the center of your skyrmion. And this dynamics, as you can see, has some sort of oscillations, which are precisely the Larmor oscillations. If you follow the trajectory of the center of the bubble, it has this interesting shape that seems to bounce of some invisible obstacle. And in fact, this trajectory is a superposition of two circular motion, as illustrated in the lower figure. And it comes about because your equation of motion for a massive particle is second order in time derivatives. And so you get two circular modes, one clockwise and the other counterclockwise, and their superposition gives you pretty much this hypocycloidal trajectory. So that again is evidence that you have a mass. And by following the trajectory, you can figure out what the mass is, what the gyroscopic constant g is, and so on. So is a skyrmion massive or massless? The naive answer to that question depends on your definition. If you choose the skyrmion density as your measure of probability, then you get the massless dynamics. And if you choose the magnetic magnetization, the longitudinal component of that, then it would appear that the skyrmion is massive. In fact, the situation is a bit more complex. Even if you choose the second definition, where the skyrmion is supposedly massive, there are situations where it behaves as a massless particle, and there are other situations where it behaves as a massive one. It depends on the nature of the external force that couples to the skyrmion. So we describe it in our paper, but in fact, an early indication of that came from an earlier paper by Roche Nagaosa and their junior colleagues, in which there's figure 1, in which you can read the following caption. When a skyrmion is driven by a time-dependent external force, it becomes distorted and the spins persist, resulting in a delayed response and a large effective mass. In other words, if you drive your skyrmion with unapplied force, like a magnetic field gradient or something like that, you get massive dynamics, they concluded. In contrast, when the skyrmion motion is driven by an electric current, the skyrmion approximately flows with the current with little distortion and precession. Therefore, skyrmions respond quickly to rapid changes of the electric current. So in that case, the dynamics appear to be massless. It was a purely numerical study. There were no arguments given why that would be the case. And so we're filling in that void, and we'll explain how exactly that happens. But before I get to that, let me briefly mention, for those of you who don't know it, what the origin of mass is in ferromagnetic solitons. Mass, in fact, or inertia, is an emergent quality in ferromagnetic solitons. They typically don't have inertia, but under the right conditions, they can get one. And that happens when one of your degrees of freedom becomes hard, as shown in this illustration. So picture a skyrmion or a vortex that is moving in a long strip of a ferromagnet, where the y direction is confined, so it's short, so the motion of the skyrmion is confined more or less to the middle line of the strip. So the potential energy rises steeply as you go away from the center of the line, but it stays more or less constant and changes very gently if you go in the x direction. So the x motion will be soft and the y motion will be hard. So we might want to integrate out the y motion because the skyrmion wouldn't move much in that direction anyway. And so here is Thiele's equation that gives the massless motion ostensibly, which when you project onto the x and y axes gives you these two equations, where we have the confining potential ky squared over 2 in the y direction, and some potential energy that depends slowly on the x direction to give you a very weak force in that direction. So the y equation of motion is this, where the velocity in the x direction gives you a Lorentz-like force, and it's balanced by the restoring potential from the confining force. So you can integrate out y by expressing it in terms of the x velocity and plug it into the equation of motion for x. And doing so gives you massive dynamics for the x coordinate, where mass times acceleration is given by the potential force acting on x. So the generic mechanism for producing mass or inertia is you start with a soft mode and a hard mode. X is the soft mode, y is the hard mode. They're coupled gyroscopically. Moving along one of these directions produces a force for the other. And then you integrate out the hard mode, and that doing so makes a mass for the soft mode. And in fact, that's a very typical scenario that was first pointed out by Dern as far back as 1948. So here we present a new model of a skyrmion as a compound of two particles. Particle 1 is visible, and it has an invisible partner, particle 2. It's invisible to the experimentalist. So the experimentalist can only probe particle 1, but particle 2 is present, and it affects the motion of particle 1. So the two particles are massless. They are confined to move in the xy plane, like a skyrmion. And they're coupled to each other in two different ways, one by an elastic spring of strength K, and the other by a slightly bizarre Lorentz force in the presence of a magnetic field. What's bizarre about it is that the force on particle 1 is given by the velocity of particle 2, and vice versa. The force on particle 2, the Lorentz force on particle 2, is given by the velocity of particle 1. All the other forces are ordinary, so the spring force connecting these particles is just K times the distance between them. And there's an external electric field that couples to both particles. They have charges Q1 and Q2. And for convenience, we've introduced the total charge of 2Q here. So these are the two equations of motion for the two massless particles. And so if we could observe both of these, that would be the end of the story. But we can only observe one of them. And so we would have to integrate out the motion of particle 2 and see what happens to particle 1 in the process. Now, to motivate this model, why exactly we would choose it, let me show that, in fact, this model is related precisely to the motion of a magnetic bubble. So here I have the bubble which is centered in equilibrium at the center of the disk. And I will use a radial coordinate r at an azimuthal angle alpha to parameterize the position of the domain wall that separates the red domain from the blue domain, this white thing. So if this domain wall gets deformed, then instead of the same radius r bar in equilibrium, the radius of the domain wall will depend on the direction, and you can expand it in a Fourier series in various harmonics in alpha. And so here you have the motion of our bubble that you've already seen. These coefficients have a very simple meaning. So A naught, for instance, is the breathing mode. You can see that the radius of the bubble changes here. A1 and B1, the first harmonics, correspond to a rigid displacement, A1 along X, B1 along Y. The second harmonics give you an elliptical deformation, and so on and so forth. So the visible particle, particle number 1, corresponds to the rigid displacement of the bubble, the displacement A1 and B1. The invisible particle corresponds to the transverse magnetization that lives on the boundary of the red domain or on the white domain wall. So you can see that right now the magnetization on the domain wall is more or less parallel to the domain wall, but it need not be the case. In fact, it can deviate from that. And so we can equally express the azimuthal angle of the transverse magnetization as a function of the polar angle alpha. And to the 0th approximation, it's simply pi/2 plus the azimuthal angle, plus the polar angle alpha. It will be pi/2 here, pi here, 3 pi/2, 2 pi, and then back pi/2 there. But if you have fluctuations, if the magnetization, the transverse magnetization deviates from that ideal position, you will have some xi and eta amplitudes that correspond to various deformations of the transverse magnetization. So xi naught would be the global rotation. A positive xi naught would mean that all the spins on this domain wall will tilt a little bit counterclockwise. Xi1 and eta1 would be the first harmonic, where you would have 2 nodes and positive and negative deviations, and so on, and so on and so forth. So the invisible particle, particle number 2, corresponds to the first harmonic of the azimuthal angle coefficients xi1 and eta1 in this particular way. So here are the modes illustrated in a schematic way. We start with an ideal bubble in which the bubble is centered in the middle. So, and the magnetization ideally points along the domain wall. So both R1 and R2 vanish. If you make a non-zero R1, let's say its X component would be greater than 0, that corresponds to displacing the bubble to the right without changing the direction of magnetization on your domain wall. So you can see that now the domain wall orientation doesn't quite match the direction of the domain wall. So there's an energy cost associated with it. Y1 corresponds to a vertical displacement in this case. And again, there are mismatches on these sides between the direction of magnetization and the domain. The other particle, the invisible one, R2, corresponds to keeping the domain wall, the bubble in place, but changing the orientation of the spins on the domain wall. And so here again, there is a mismatch because the bubble has not shifted, but the magnetization turned, and in this case as well. Okay, so back to our model. It turns out that this model has exactly the same dynamics as the dynamics of a magnetic bubble, which we investigated previously, concluded that it was massive for certain types of forces. And the equations of motion are like this. For the equation of motion for the visible partner is this, and for the invisible one, it's that. So we can introduce more convenient variables, the center of the two particles, which would be called the guiding center here, because there is no mass yet, right? So we can call it the center of mass, and the relative position, which is the difference of the two. And you can write the equations of motion for the relative position and for the guiding center, and they will look like this. And you can see that the relative position couples to the electric field through the difference of the charges, whereas the guiding center couples to the external electric field through the sum of the charges Q1 plus Q2. So if you say, okay, suppose I choose the relative motion to be the invisible mode, and I integrate it out, the two equations are completely separate. So integrating out the relative motion has no effect on the guiding center. And so you would then obtain a completely massless motion for the guiding center. But I want to remind you that it's not the relative position that's invisible to us. It's the position of particle 2 that's invisible. So we'll have to integrate out position R2 instead and see what it does to R1. So here are what the guiding center is. In fact, it corresponds to a rigid displacement of the bubble with its magnetization. So you displace the bubble, the MZ component, and you also have a matching change for the transverse component. So that's basically just a translation of the bubble, both the longitudinal and transverse components, either along X or along Y. The relative motion corresponds to doing the same thing. You change both, but out of phase. And so you can see there's a great mismatch between the orientation of the domain wall and the magnetization on it. Okay, so we take our equation of motion for particle 1 and particle 2, and we integrate out the motion for particle 2. So we can take this equation where R2 can be expressed in terms of R1, R1 dot, and the electric field, and then we plug it into the first equation to get this equation of motion for particle 1 alone, the one that we can control and measure. So this equation has the usual form expected with a mass, with a coupling to the magnetic field, now the normal one, proportional to its own velocity, coupling to the external electric field with a different charge now. It used to be Q1, and now it's the sum of the two charges because the electric force pulls both electric charges. And so if we integrate out particle 2, then its electric force is transferred to particle 1. But notice that there is an additional term that changes the dynamics somewhat. That's a rather unusual force in which the force is proportional to the cross product of the time derivative of the electric field and the magnetic field. And it's proportional to charge Q2 as well. So the presence of this force can modify the dynamics of this supposedly massive particle and mimic a massless motion, it turns out. We will see how that can happen. Now, let's consider a couple of illustrating examples. One in which the visible particle couples to the electric field, but the invisible one does not, so its charge is 0. So here are the two equations. The visible particle has a coupling to the electric field, and the invisible particle does not. So you integrate out the invisible particle, and your visible particle has a very simple dynamics. Mass times acceleration equals the Lorentz force plus the force from the electric field, and there are no funny terms. So this should exhibit Larmor oscillations, and the dynamics will be massive, as we will conclude. Another way to see why there are no Lorentz, why there are Larmor oscillations, is to look at the equations of motion for the guiding center and for the relative position. It is in fact the relative position that is responsible for the Larmor oscillations, because remember, the Larmor oscillations had the frequency proportional to the strength of the strength of K divided by the strength of B. So it's the Larmor oscillations come from this. So if your relative motion is coupled to the external force, you turn on suddenly the external force, and then your relative position gets shifted, and that's where you get the Larmor oscillations from. And so it will be visible in the motion of your particle. So that's another way to see it. The relative motion couples to the external force, and the sudden onset of the external force gives rise to Larmor oscillations. And although the guiding center doesn't see these oscillations, it has a massless dynamics. It's not the guiding center that we probe. We probe particle 1, whose coordinate is the sum of the guiding center divided by 2 and the relative coordinate. So the relative coordinate has Larmor oscillations, and therefore particle 1 has Larmor oscillations as well. So that's the usual case. That's what happens when you excite a skyrmion bubble with an applied magnetic field. It only couples to the longitudinal component of MZ. It doesn't couple to the transverse components, which are the invisible particle. Now, here's a different case where both particles couple equally strongly, equal charges to the electric field. And then when you integrate out particle 2, this is the equation you get. And in fact, this equation happens to be finely tuned in an interesting way. In fact, you can split this equation into two compatible equations, which use 2 out of 4 terms in this equation. The middle terms happen to be 0 on their own, and the external terms, so to speak, the outside terms, also happen to be 0 on their own. In fact, one equation is a consequence of the other. So if you take the first equation and differentiate with respect to time, you'll get the second equation. Here you have the first derivative of velocity or position 1. Here you have the second derivative, and here you have the electric field, and there you have the electric field time derivative. So in fact, these two equations are compatible, provided that you have exactly this condition for charges. So that seems like fine-tuning, but there is an easier way to understand this. If the charges are equal, then the relative motion has 0 coupling to the external electric field. So even if you turn on the external force, the relative motion will not know anything about it. And if it was not excited to begin with, Larmor oscillations will not happen. And so R1 will be the same as R2 because R relative is 0. And so both particles, the visible one and the invisible one, will follow the center of the guiding center trajectory, which shows no oscillations whatsoever. And so you will have an impression that your visible particle behaves as a massless object. Here are the connections to our bubble. We can excite the motion of a bubble with an applied longitudinal magnetic field that has a spatial gradient. If you apply just the uniform magnetic field, then the bubble will change its radius, but it will not shift. Having a gradient creates a potential energy landscape that is linear in the position of the bubble, and so you will have an external force pushing the bubble. You can see here that the potential energy only depends on R1, which is not a coincidence, since R2 comes from the transverse components of the magnetization. They don't couple to the field along the z direction, and therefore the potential energy only depends on R1. So particle R2 will have no knowledge about this external force, and that's equivalent to having Q1 non-zero and Q2 equal to 0. So the charges are unequal. The relative motion couples to this external field, and therefore the visible particle will have massive oscillations or Larmor oscillations, a hallmark of massive dynamics. In contrast, if you use spin transfer torque, your Landau-Lifshitz equation gets modified in this way. J is the electric current density, dotted with the gradient of magnetization. Capital P is the polarization of the spin in the electrical current, which you can express in terms of an effective velocity. S is the spin density. So U is the effective velocity with which the electrons are flowing in the current. And then the equations of motion will have this form. And you can see that the external force comes from the cross product of U and EZ. And so that will be sort of the coupling to the electric field or potential force. And you can see that both particles couple equally. So the charges are equal, and therefore relative motion will not couple to the external force, in this case, to the spin transfer torque. And so there will be no Larmor oscillations, and the response to the electric current, more precisely to spin torque from it, will be massless. There will be no Larmor oscillations. Again, another way to put it is to look at the equations of motion for normal modes. You can see that the guiding center couples to the current or spin torque from current, and the relative position does not. So it knows nothing about it. And turning on suddenly the electrical current does not produce the oscillations of relative motion. So no Larmor precession and massless dynamics, therefore. So we come to the end of my talk. I'll have 2 pages of conclusions. One is answering the question, is skyrmion dynamics massive or massless? The answer is not quite simple. It depends on quite a number of things. First, it depends on how the skyrmion position is defined, whether it's defined in terms of the first moment of the skyrmion density, in which case you will observe massless dynamics, like in Thiele's equation. And if you define it in terms of the first moment of the magnetization, the longitudinal magnetization of the bubble, the center of the bubble, basically, its MZ component, you seem to get massive dynamics, sometimes massless dynamics, sometimes. The answer, whether which one it is, depends further on the nature of the driving force. A longitudinal Zeeman field with a gradient will create a massive dynamics, and an adiabatic spin transfer torque will give a massless dynamics. So exactly as Nagels and Roche conjectured on the basis of their numerical study. Second set of conclusions is an invention of a new mechanical model, a weird one slightly, with a massless charged particle that has an invisible partner that is also massless and charged. The visible particle represents longitudinal magnetization of the skyrmion bubble, and the invisible one represents the transverse magnetization. The two particles are coupled in two ways, by a spring and by a weird gyroscopic force, in which the force on one particle is proportional to the velocity of the other. If both couple equally strongly to an external force, then the relative motion of the two particles is not excited. They move as a guiding center, and the guiding center has massless dynamics. So that's how you can get massless dynamics. And that happens with spin transfer torque. Otherwise, if the two particles, visible and invisible, coupled to an external stimulus in different with different strengths, then the relative motion will couple to it, and there will be Larmor oscillations. So that will create an impression of a massive particle. So that is the end of my talk, and I will be happy to answer any questions if you have. Thank you.
Okay, thank you very much for the wonderful talk, Oleg. So, yeah, I think the talk is now open for the question, and I think there should be lots of questions now. So, who would like to start? Yeah, okay. Let's start the second one.
Yep. Thanks for the nice talk. So this this nature of this mass, depending on the nature of these external forces, means that the mass of skyrmion is not intrinsic, right?
Well, it's an intrinsic in the sense that it can be derived here. But if you perhaps look at it from the following perspective, from this perspective, you get a mass, okay, by integrating out one of the particles. However, in addition to a mass and the renormalization of the electric charge, integrating out the partner produces a funny new force. And this funny new force can mask the presence of the mass. You can interpret it that way. So the kinetic energy is definitely there, but it can be masked by the presence of additional forces that appear like so.
So also this strange force E dot cross B. How can you what's the physical meaning of it? So, would there be any analog of this force?
That's a good question.
In real material, real particle.
I've not thought about this, and it only occurred to me today, in fact, that perhaps someone has already figured out that there is such a force in some other context. It usually happens. So one needs to look deep into the literature and see if anyone has ever come up with such a force. That would be interesting. So I've not come across it, but it's just my ignorance, and my ignorance is vast, as you know. You and I have discovered a few things, rediscovered a few wheels together, right?
Yeah, that's right. Also, the last question is about the how about the non-adiabatic spin transfer torque?
So I've deliberately stayed away from other types of forces and torques. So I've not included dissipation, because it turns out that dissipation has nothing to do with the emergence of the mass. The mass emerges because you have a gyroscopic force and a conservative force. And basically, these are the two ingredients you need to create mass, inertia, or kinetic energy. Dissipation is a completely separate question. And in fact, we explored what happens if you add non-adiabatic spin transfer torque or some dissipation. And it just, there were no crisp answers, and it was not particularly useful to go into it. I mean, from the practical purpose, maybe. But, a dissipation of which non-adiabatic spin transfer torque is an example, it will give you some damping. And so your Larmor oscillations will be underdamped, maybe even overdamped. But the oscillations will still be there if they're underdamped.
Okay, got it. Okay, yeah, thank you.
Okay, other questions and comments? We still have some time.
Yeah, the sun has already set in Baltimore, so I have to turn on the lights.
So I have a question.
Okay, please go ahead.
So this mass, would you think this inertia mass would be, since the skyrmion is a mesoscopic object, would it be of the order of one of the electrons, or whatever contains the spin, or would it be something large?
It would be something large. If I remember correctly, for a skyrmion bubble, which is a large radius skyrmion, the mass scales with the length of the domain wall. So it's not one skyrmion mass, one electron mass. It's much, much larger than that. So it's a fairly heavy object.
Thank you.
Yeah, actually, I have one question. So at the beginning of your talk, you mentioned this skyrmion deformation, which I guess can also reasonably be described as the magnum bound to the skyrmion. So, I mean, how much does that contribute to mass? I mean, what kind of relation can we establish?
Well, it's precisely that, right? So you have different modes, and you can imagine the breathing mode, right, where the skyrmion just changes its radius. Then you can have the first harmonic would be simply rigid displacements. The second harmonics would be elliptical deformations. Third harmonic would be trifoil deformations, and so on. Right? You have to consider these deformations. You can think of these as spin waves on the surface of the bubble. And in addition to them, you have to consider the transverse fluctuations of the magnetization on the boundary. And each of these harmonics with some azimuthal number m of the longitudinal part is coupled gyroscopically to the transverse fluctuations with the same azimuthal number. So in fact, the mass for the longitudinal motion for the displacement of the bubble in the x and y direction comes from integrating out the corresponding first harmonics in the transverse magnetization. So you integrate out these magnons, and that's what gives the mass to the translational motion.
I see. I mean, yesterday, Matthias Chloe gave a talk where he was talking about the skyrmion pinning. And from the language you're using, I mean, from what you were just telling us, it seems like he was really saying that, you know, it's really the skyrmion, these internal magnon modes that are spin wave modes that are really contributing to this. That's really making the major contribution to pinning. I mean, what you have presented in your talk now. I mean, can that give any insight to what he was seeing experimentally?
That's a good question. I don't have an answer right now, so I'll have to think about it and talk to Matthias.
Yeah. Okay, we still have a couple of minutes. So, I think we can take like one more question. I mean, we have some skyrmion experimentalists in the audience, like Professor Ji-Hoon Kim, or maybe he's not around right now. Yeah, so just one brief question. So I suppose, I mean, skyrmion can also carry heat current.
Mhm.
Can that be related to, I mean, so would that require like this, yeah, so would that require this kind of mass, skyrmion being massive?
Well, yeah.
I mean, especially since you're establishing this connection with the internal mode.
Right. Yeah. So for a longitudinal magnetic field, the answer is easy to give because longitudinal field couples to the longitudinal component of magnetization, but not to the transverse one. So there it's clear that the visible mode gets coupled to that force and the invisible mode does not. For the electric current, you know, the spin transfer torque couples to both. It doesn't matter in which direction the spins point. It's not obvious that the coupling should be of equal strength, but it happens to be the case. So you would have to do a calculation. I'm pretty sure that both components, longitudinal and transverse, will couple to a heat current. Whether the strength is the same, I cannot tell without doing the calculation. So chances are that it may also give you a massless response.
Okay, thanks again to Oleg for his wonderful talk.
I have a quick question.
Okay.
Okay, I'm Ki-Seok Lee. I'm very interested with your theoretical results. So for me, it's the mass might be related to the two modes, breathing mode and the gyrotropic mode of the skyrmion. So is there any kind of a relations between that? So sometimes when we excite one mode only, but sometimes another mode excite both modes excited, and then we can see such kind of a breathing, the mass related motion. So is there any connections between?
Yeah, at least at the harmonic level, you expand your energy or the Lagrangian better in terms of these amplitudes that I had on the screen. At least at the harmonic level, when things are only quadratic in these amplitudes, modes with different azimuthal numbers are not coupled. So the breathing mode is not coupled to the translational motion. And so translational motion cannot gain the mass from integrating out the breathing mode. Maybe there are some nonlinear effects, but that would have to be a large amplitude of breathing mode that could potentially contribute, but by symmetry, I would say no.
Okay, thank you.
Okay, thanks again to Oleg, and I think we need to move on to our next speaker.